Imagine walking in one direction and never turning. You check your bearing constantly. The ground never changes. No wall ever appears ahead, and every map you draw of the land around you comes back perfect. Then one afternoon you look down, and there are footprints heading the same way you are, at your exact stride length, and they are yours. Nothing was wrong with your maps. They were flawless, and they were completely silent about the only thing you wanted to know. We are in that position tonight. We have measured the shape of space to 2 parts in 1,000, and the answer is that space is flat. Almost every account you have read follows that with a sentence which is not in the data. Therefore, the universe goes on forever. It does not follow. Space can be perfectly flat and still finite, closing back onto itself with no edge anywhere, and no measurement made from the inside could ever tell. Get comfortable. Hit subscribe if this is your first time here, because by the end of tonight you will know why the shape of the universe is the most mind-bending question in physics, and why the answer may be a fact about the room you are lying in that nobody will ever be told. Now, let's slowly ease into this. Part 1. The word that is 2 words. Space has a shape, and we have measured it. That sentence is true, and almost everything people take from it is not. The measurement is real. It is one of the most precise things our species has ever done, carried out with instruments flown above the atmosphere and satellites parked 1.5 million kilometers from Earth, and the answer came back clean. Space is flat, not approximately flat, not flat for practical purposes, but flat to within 2 parts in 1,000. Which is a level of confidence most of physics would envy. You will find that result quoted everywhere, usually followed immediately by a second sentence that says the universe must therefore go on forever. That second sentence does not follow from the first. It never did, and the people who made the measurement have been saying so, in print, for 1/4 of a century. The gap between those 2 sentences is what tonight is about, and it is wider and stranger than almost anyone outside the field realizes. The problem starts with the word shape. It sounds like one thing. It is 2, and they are close to independent of each other. The first meaning is curvature. Curvature is a local property, which means it is a fact about the immediate neighborhood of a point. If you stand somewhere in space and draw a very large triangle, curvature is what decides whether the angles add up to 180 degrees. It is what decides whether 2 parallel lines stay parallel forever, or slowly converge, or slowly separate. It is what decides whether a circle of a given radius has quite as much circumference as you expected. Curvature is measurable from inside. You do not have to leave, or look at the whole thing from outside, or know anything at all about the parts you cannot see. You can determine it in a small patch, and the answer you get in that patch is genuine. The second meaning is connectivity. Connectivity is a global property, which means it is a fact about how the whole thing is joined together. It asks whether space closes back on itself, and if so, in how many directions, and after how far, and with what sort of twist in the join. It asks whether a straight line, followed patiently enough, brings you home. And here is the difficulty that runs through the entire night. Connectivity leaves no trace in any local measurement whatsoever. Not a faint trace. None. There is a demonstration of this on your desk, if you have a sheet of paper on it. Take the sheet and look at it. The geometry is flat. Every triangle you draw on it has angles that sum to 180 degrees. Every pair of parallel lines behaves. Every circle has exactly the circumference the formula says. Now roll it into a cylinder and tape the edges together. Look at the geometry again. Nothing changed. Not a little, not subtly, nothing. Every triangle drawn on the surface still sums to 180. Every circle still has the circumference it had. If you were a creature living inside that surface, small enough that you never noticed the roll, no measurement available to you would reveal that anything had happened. The paper's geometry is untouched. What changed is the connectivity, and connectivity is invisible from close up. Imagine you are that creature. You live on a flat world, and you are very good at surveying it. Your triangles are perfect. Your parallel lines never meet. Your maps are exact to the width of a hair, and they have been checked and rechecked by every measurement your civilization can devise, and they agree. So you decide to settle the last question. You will find out how far it goes. You set out walking, and you pick a direction, and you commit to it. You check your bearing constantly. You never turn. The point is not the distance, it is the discipline, and you keep the discipline for years. The land goes on. Nothing about it changes. There is no wall ahead, no thinning of the ground, no sign anywhere of a limit approaching. Your maps stay accurate. Every survey you take confirms the same flat geometry you have always measured. And then one afternoon you look down at the ground in front of you, and there are footprints in it, walking in exactly the direction you are walking, at exactly your stride length, and they are yours. Nothing was wrong with your maps. That is the part worth sitting with. Your maps were not slightly wrong or subtly incomplete. They were perfect, and they were also completely silent about the thing you most wanted to know. You had a flawless local description of a world whose global structure it could not describe. You had a perfect map that said nothing about the edges because there were no edges to say anything about, and the map had no way of telling you that either. We are in that position now, not metaphorically, not approximately. We have measured the curvature of space with instruments that took decades to build, and the answer is excellent. And it is a statement about the local geometry, and the question of whether a straight line brings you home is untouched by it. People have been circling this for a very long time, without the language to say it. In the 4th century before the Common Era, a Greek philosopher named Archytas of Tarentum posed a problem that has never quite gone away. Suppose the universe has an edge. Walk to it. Now stand there and thrust out a spear. Either the spear goes, in which case there was space beyond, and that was not the edge, or something stops it, in which case there is something there, and that something is also part of the universe, and again that was not the edge. Lucretius restated the argument 3 centuries later in his long poem on the nature of things, and it has been restated in some form in every century since, because it is a good argument. What matters about it, once you know to look, is that it is not a geometrical argument at all. Archytas is not saying anything about how space curves. He is saying something about how space is joined, or rather about the impossibility of it terminating. He is doing topology, in the 4th century before the Common Era, with a spear. The same intuition surfaces again in the 15th century, in a line from Nicholas of Cusa, a German cardinal writing in 1440. He described the universe as a thing whose center is everywhere and whose circumference is nowhere. Read casually, it sounds like mysticism. Read carefully, it is a precise description of a homogeneous space with no boundary, and it is 400 years ahead of any mathematics that could support it. Cusa had no way to know that the sentence was technically accurate. He simply could not find a way for it to be otherwise. So the shape of the universe is really 2 questions wearing one coat. How does space curve, and how does space connect? And physics, working extremely hard for about a century, has answered the first 1 to 2 decimal places, and has not answered the second one at all. That is not a criticism. The first question turned out to be answerable, and the second may not be, but the 2 get reported as though they were the same question. And the result is that the single most repeated fact in popular cosmology quietly means something other than what almost everyone thinks it means. Tonight we are going to take that apart slowly. We will go through exactly how the flatness of space was measured, because it is a genuinely beautiful piece of work, and it deserves to be understood before it is complicated. We will find out what it does and does not license you to conclude. And then we will follow the second question, the one about connection, out to the place where it currently sits, which is somewhere very strange indeed, because the answer to the first question was published and celebrated and put in the textbooks, and the answer to the second one might not be available to anybody, ever, from anywhere inside this universe. Part 2. What flat actually means. Curvature is not something you can see by looking at space. It is something you infer from the behavior of things inside it, and the behavior in question is disarmingly simple. Take a triangle. In the geometry you were taught at school, the interior angles of a triangle add up to 180 degrees, and they do this regardless of how large or small the triangle is, or where you draw it, or how you orient it. That constancy is not a fact about triangles. It is a fact about the space the triangle is drawn in, and it is one of several equivalent ways of saying that the space is flat. Now draw a triangle on the surface of a sphere. Start at the North Pole. Head south along a line of longitude until you reach the equator. Turn 90 degrees and travel a quarter of the way around the equator. Turn 90 degrees again and head back north until you arrive at the pole. You have drawn a triangle with 3 sides, each one a straight line as far as the surface is concerned, and its angles are 90 plus 90 plus 90, 270 degrees. 90 degrees more than the answer you were taught. On a triangle, you can draw on a beach ball. That excess is the curvature, and it is positive. On a positively curved surface, triangles carry more than 180 degrees, lines that start out parallel, converge, and eventually cross, and a circle of a given radius has less circumference than the formula predicts. There is less room out there than you expected. The surface of a sphere also has a property that will matter enormously later tonight. It has finite area, and it has no edge. You can walk on a beach ball forever, and never fall off it, and never come to a wall. The opposite case exists too. On a negatively curved surface, which people usually picture as a saddle or the flare of a trumpet bell, triangles carry less than 180 degrees, lines that start out parallel drift apart, and circles have more circumference than they should. There is more room out there than you expected, and the excess grows the further out you go. 3 options then: positive, negative, flat. And the reason this taxonomy exists at all is a 2,000-year argument about a single sentence. Euclid wrote down 5 postulates, and 4 of them are the sort of thing nobody argues with. A straight line can be drawn between any 2 points. A line segment can be extended. A circle can be drawn with any center and radius. All right angles are equal. Then comes the 5th, and the 5th is a mouthful. In its cleanest later form, it says that given a line, and a point not on it, there is exactly one line through that point, which never meets the first. Exactly one, not 0, not 2, not infinitely many, 1. Mathematicians found the 5th postulate ugly for 2,000 years. It was longer than the others, less obvious than the others, and it felt like something that ought to be provable from the first 4, rather than assumed. Generation after generation tried to prove it. Every single one of them failed, and a surprising number of them failed by accident in the same way, by quietly assuming something equivalent to the 5th postulate somewhere in the middle of the proof, and not noticing. Then, in the 1820s and 30s, 2 men, working independently and without knowledge of each other, stopped trying to prove it, and asked what would happen if it were false. Nikolai Lobachevsky in Kazan and János Bolyai in Hungary both constructed complete and internally consistent geometries in which infinitely many lines through the point never meet the original. No contradiction appeared. No contradiction ever appeared. The 5th postulate is not a theorem. It is a choice, and other choices produce perfectly sound worlds. Bolyai's father, himself a mathematician, had spent years on the problem, and had written to his son begging him to leave it alone, telling him it would consume his life and leave him with nothing. When János succeeded, his father sent the work to an old friend for an opinion. The friend was Carl Friedrich Gauss, and Gauss replied that he could not praise the work, because to praise it would be to praise himself, since he had reached the same conclusions decades earlier and had never published a word of it. He had not published because he expected to be laughed at. In a letter, he described his reluctance in terms of the clamour of the Boeotians, the Boeotians being the ancient Greek byword for people too dull to understand what they were hearing. The most capable mathematician of his century sat on a result for 30 years because he did not want to argue with the slow. There is a story about Gauss that gets told in almost every popular account of this subject, and it is worth telling here, mainly so we can take it apart, because the correction is more interesting than the story. The story goes that Gauss, during his survey work in Hanover in the early 1820s, measured the angles of an enormous triangle between three mountain peaks, the Brocken in the Harz, the Hohehagen near Gottingen, and the Inselsberg in Thuringia. The triangle was huge, tens of kilometers on a side, and the story says he did it in order to test whether physical space is Euclidean, to find out, in other words, whether the universe itself obeys the fifth postulate. It is a wonderful story. It is also, according to historians who have gone through the correspondence and the survey records, not true. Gauss did measure the triangle. He measured it because he had spent years patching together a network of 26 smaller triangles across the survey region, and he needed a large independent check on the accumulated error, and because he was interested in how much the Earth departs from a perfect sphere. The purpose was geodesy. It was a quality control measurement on a map. The story appears to have grown out of a passage in a memoir published in 1856 by Sartorius von Waltershausen, who knew Gauss personally. What Sartorius actually wrote was that Gauss regarded the measured angles as consistent with the fifth postulate. That is a remark about what the numbers showed. Somewhere in the retelling, it turned into a statement about why the measurement was made, and it has been repeated ever since. The myth survives because it is entirely believable, and it is believable for a reason that matters. Curvature really is measurable that way. If you draw a large enough triangle and measure its angles precisely enough, you get a genuine answer about the geometry of the space you are in. Gauss could not have detected the curvature of space with survey instruments in Hanover, because the effect at that scale is unimaginably below the noise, but the method is sound. Scale it up far enough, and it works. In about 180 years, someone would scale it up far enough, and they would do it with light that had been traveling since before there were atoms. That is the half of the shape question that turns out to be answerable. Everything in this part of the story is about geometry that can be settled from inside a small patch by a creature who never leaves, using triangles and rulers and patience. It is a real achievement, and we are going to see exactly how it was pulled off. But notice what none of it touches. Lobachevsky, Bolyai, Gauss, the fifth postulate, the Great Triangle in Hanover. All of it is about how space bends near a point. Not one line of it says anything about whether the space closes back on itself. And there was a man, sitting in a lecture hall in Gottingen, about to point out that these are not the same question, and that answering one of them tells you nothing about the other. He was 27 years old, and he was terrified. Part 3. Riemann's Sentence. Gottingen, the 10th of June, 1854. Bernhard Riemann is about to give the worst prepared and most important lecture of his life. The occasion is a habilitation, the German academic ritual that qualifies a scholar to teach at a university. The candidate submits 3 possible topics for the trial lecture, ranked in order of preference, and the faculty chooses one. By long custom, the faculty chooses the first. Riemann had prepared the first 2 thoroughly, and had put down, as the third, a subject on the foundations of geometry that he had barely begun to think through. It was a formality. Nobody picks the third. Gauss picked the third. Gauss was 77 and had roughly 14 months to live. He had been sitting on his own unpublished thoughts about non-Euclidean geometry for half a century, and when he saw the topic on the list, he took the opportunity that had arrived in front of him. Riemann had about 7 weeks. He also had a physics project running at the same time, and by his own account he made himself ill working on both. What he produced in those 7 weeks is one of the small number of documents that genuinely changed what people are able to think. The lecture is called On the Hypotheses Which Lie at the Bases of Geometry, and Riemann had to deliver it without equations, because the audience was the full philosophical faculty rather than the mathematicians. He had to describe the machinery of curved, multidimensional spaces in ordinary German prose to a room of philologists and historians, one of whom was the greatest mathematician alive. What he built in that lecture is the framework that general relativity would eventually be written in, 60 years before anyone needed it. He described how to define a geometry on a space of any number of dimensions, using nothing but a rule for measuring small distances at each point. He showed that curvature is intrinsic, meaning it belongs to the space itself and can be detected by creatures living inside it, with no need for the space to be sitting inside some larger space that it curves into. That last point is worth pausing on, because it is the thing most people's intuition refuses. When you picture curved space, you almost certainly picture it bending into something. Riemann showed that the bending needs no outside. The curvature is a set of relationships among the measurements taken inside, and it is complete on its own terms. And then, near the end, he says the thing that this entire night has been arranged around. Speaking about what happens when you try to extend geometry to the very large, he says that we must distinguish between unboundedness and infinite extent. The former, he says, belongs to the relations of extent. The latter belongs to the relations of measure. Read that again, slowly, because it is doing a great deal of work in very few words. Unboundedness means having no edge, no boundary, no place where the space stops. Infinite extent means going on forever, having no total size, containing an endless amount of room. These sound like the same thing. In everyday life they behave like the same thing, because the everyday examples of unbounded things are also endless things. Riemann's point is that they are two different kinds of property. One is about how the space is arranged, the other is about how much of it there is, and nothing whatsoever forces them to travel together. He gives the immediate consequence himself. If space has constant positive curvature, however slight that curvature might be, then space must necessarily be finite. It would be unbounded, with no edge anywhere, and it would have a definite total volume, both at once. Not a paradox, not a trick of language, just two independent properties taking independent values. Consider what it took to say that, in 1854, nobody had measured the curvature of anything larger than a country. The word galaxy did not yet mean what it means now, and the argument over whether the spiral nebulae were inside the Milky Way or were separate systems would not be settled for another 70 years. There was no evidence of any kind bearing on the question. Riemann was working it out from the structure of the concepts, and what he worked out was a distinction that 170 years of instruments have not managed to collapse. There is a way to feel the distinction, rather than just accept it. Think of the difference between asking how a road is arranged and asking how long it is. A circular racetrack has no ends. You can drive it for the rest of your life and never arrive at a barrier, never find a place where the tarmac stops and something else begins. That is a fact about the arrangement. It is completely separate from the question of whether the lap is 2 kilometers or 200, and no amount of driving in a small section of it Measuring the camber and the width and the radius of the bends will tell you the lap length. Riemann's claim is that space is allowed to be like the track, endless in the sense of having no barrier, and finite in the sense of having a total. The problem had defeated better-known people. Immanuel Kant, in the Critique of Pure Reason, offered the question of whether the universe is finite or infinite, in extent as the first of his antinomies, a pair of arguments that appear to prove both answers, and therefore, he concluded, demonstrate that the question is malformed, and that human reason has overreached itself in asking it. Kant did not have the option Riemann later found. He was working with a concept of space in which unbounded and infinite were welded together, so the two arguments really did collide. Separate the properties, and the antinomy loosens considerably. What Kant took to be a limit of reason turns out to have been a limit of vocabulary. The lecture did not immediately land. Gauss, by the accounts we have, was unusually moved by it, and spoke about it with enthusiasm on the walk home, which for Gauss was extraordinary behavior. The rest of the room mostly did not follow. Riemann did not publish it. It sat in a drawer, and it was printed in 1868, 2 years after he died. He died in July of 1866, in Italy, where he had gone, in the hope that the climate would help his tuberculosis. He was 39 years old. He had been ill for years, and had been travelling south whenever he could afford to, and had been working the entire time. The lecture had been sitting unpublished for 12 years. And here is what makes this the emotional centre of the first half of tonight, rather than a piece of biography. The most precise statement anyone has ever made about the shape of the universe was made by a 27-year-old with no data in a lecture he did not want to give, on a topic he expected nobody to choose, and it was correct, and it is still correct, and every instrument built since has failed to improve on it. We can now measure the curvature of space to 2 parts in 1,000. We have satellites at gravitationally stable points, and detectors cooled to 1/10 of a degree above absolute zero, and datasets that took decades of international effort to assemble. And when the results come in, the correct way to interpret them is still exactly the way Riemann said it would be in 1854. Unboundedness and infinite extent are not the same property. Measuring one does not deliver the other. There is something almost uncomfortable about that. We tend to assume that thinking gets superseded by measuring, that the philosophers hold the ground until the experimentalists arrive and then hand it over. Here the thinking arrived first and never had to move. The measurements came, and they were superb, and they slotted into the space Riemann had already marked out for them, and the part he said they could not settle is still not settled. He also, incidentally, was the first person to suggest in print that the geometry of physical space might be determined by the matter in it, and that the question of what geometry space actually has is a question for physics rather than for mathematics. Einstein would spend a decade arriving at that. But the distinction is the thing. 2 properties, not 1. No edge, and how much there is. Hold on to it, because in about an hour, it is going to come back with a great deal more weight on it. 61 years after that lecture, a physicist in Berlin sat down to apply his new theory of gravity to the universe as a whole, and ran directly into the wall Riemann had described. He handled it in a way that seemed at the time like a technical fix. It was actually the moment the shape of the universe stopped being a question about mathematics and started being a question about physics. And the reason he had to do anything at all was that his equations demanded to know what happens at the edge. Part 4. The edge that cannot exist. In 1917, Albert Einstein sat down to do something nobody had ever seriously attempted. He was going to write down the universe. He had finished the general theory of relativity 2 years earlier. The equations describe how the presence of matter and energy determines the geometry of space-time, and how that geometry in turn determines how matter and energy move. They had already been applied to the orbit of Mercury and to the bending of starlight near the Sun, and they had worked. Now Einstein wanted to apply them not to a planet or a star, but to everything at once. He ran into a problem immediately, and it was not a problem of physics in the ordinary sense. It was a problem about the shape of the thing he was solving for. Differential equations of the kind that appear in general relativity do not have unique solutions on their own. They tell you how a quantity changes from place to place, but to pin down an actual answer, you also have to specify what the quantity does at the limits of the region you are working in. Those specifications are called boundary conditions, and every physicist learns to write them down without thinking. If you are solving for the temperature in a metal bar, you state the temperature at both ends. If you are solving for the shape of a drumhead, you state that the rim is held fixed. Einstein was solving for the universe, and the universe does not have ends. He tried the obvious approach first, which is to specify what the geometry does at spatial infinity. Let the metric approach some definite standard form very far away, and solve inward from there. It works mathematically. It also, in Einstein's view, ruined the theory. Fixing the geometry at infinity means importing a structure that no matter is responsible for, a background that is simply there, defining what counts as being at rest and what counts as accelerating, independently of anything material. That was precisely the thing he had built general relativity to eliminate. He had spent a decade trying to make inertia a relationship between masses rather than a relationship between a mass and an empty stage. And here was the empty stage walking back in through the boundary conditions. There is a deeper version of the difficulty, and it is worth stating in its own right, because it never goes away, even now. Suppose the universe genuinely has an edge, not a horizon, not a limit on what we can see, but an actual boundary to space itself, a surface past which there is no more space. Physics is a set of rules for what happens next. At every ordinary point in the universe, those rules take the current state and produce the state a moment later, and they do it using information from the neighborhood of the point. At a boundary, half the neighborhood is missing. The rules would have to be told, separately and by hand, what to do there. Something would have to specify what happens at the wall, and that specification could not come from inside the universe, because the wall is where the inside stops. This is Archytas, with his spear, restated in the language of field equations. Either something is on the other side, in which case that was not the boundary, or nothing is on the other side, in which case the laws of physics require an instruction that no part of reality can supply. An edge is not an unlikely feature of the universe. It is a feature that would make the universe not describable. Einstein's response was to remove the problem rather than solve it. If the difficulty is boundary conditions at infinity, then build a universe with no infinity to have conditions at. He proposed that space is the three-dimensional analog of the surface of a sphere, closed, finite in total volume, and possessing no boundary anywhere at all. Travel in any direction, and you never encounter a wall, because there is no wall. Travel far enough, and you come back to where you started, because the space closes. Finite and unbounded, in the same breath. It is Riemann's distinction, 63 years later, made into a physical hypothesis about the actual universe by someone who needed it to make his equations behave. There is no center to such a space, which is the part that gives people trouble. On the surface of a ball, no point is the middle. Every point is equivalent to every other, and the apparent center of the ball is not on the surface at all. It is somewhere the surface dwellers cannot reach and do not need. The three-dimensional version works the same way. There is no place in Einstein's universe where you could stand and say the expansion started here. There is something here worth noticing, because it explains a habit of thought that persists today. For roughly the first decade of relativistic cosmology, The closed and finite universe was the default. It was what Einstein had proposed. It was the option that made the equations well-behaved, and it was the option that took the boundary problems seriously. Willem de Sitter produced a rival solution the same year, empty of matter and infinite in extent, and the two models were argued over for years. The infinite, simply connected universe that most people now assume without thinking is not a discovery that displaced the closed one. It became standard gradually, as the expanding solutions took over and as the mathematics of an infinite flat space proved easier to work with. It is a convention that hardened. Nobody ever went out and found evidence that space does not close. The irony sharpens when you look at how the closed model was described at the time. Eddington, writing for a general audience in the 1920s, spent pages carefully explaining to readers that a finite universe does not have an outside, that there is no shell and no edge and nothing beyond, and that the word finite here refers only to total volume. That explanation used to be a standard part of educating the public about cosmology. At some point it stopped being taught, and the picture that replaced it was the endless one, and the reason for the replacement was never an observation. The model also had a flaw that Einstein knew about and disliked. A finite universe full of matter should collapse under its own gravity, and the sky was not collapsing, so he added a term to the field equations, a constant that acts as a mild outward pressure everywhere in space, tuned exactly to hold the whole arrangement still. The cosmological constant. He was not happy about it, but the alternative was a model that fell in on itself in an obviously incorrect way. Within about a dozen years, the static model was finished. Friedmann had shown in 1922 that the equations permitted expanding and contracting solutions. Lemaitre had connected those solutions to the observed redshifts of the nebulae, and Hubble's measurements had made the expansion difficult to argue with. Einstein dropped the constant. The story that he called it his greatest blunder comes to us second-hand and may not be accurate, but he certainly abandoned it. The static model died, the structural insight did not, and it is still standing. That insight is this: the universe cannot have an edge, not because we have looked and failed to find one, but because an edge would demand something that physics cannot provide. So whatever shape space has, it is a shape without boundary. That leaves two families of possibility, and only two. Either space goes on forever, or space closes back on itself. There is no third option in which it simply stops. Notice how much that narrows things and how little it settles. We have eliminated the wall, which is the picture almost everyone's imagination reaches for first. What remains are two completely different universes, an endless one and a finite one that wraps. Both have no edge. Both are consistent with everything Einstein wrote down in 1917, and, as it turns out, with everything measured since. Which returns us to the practical question, and it is a hard one. If there is no edge to find, and no center to stand at, and space might curve or might not, how would you ever determine the shape of the thing you are inside of? You would need a ruler of known length, sitting at a known distance, in a place where you could measure the angle it makes, and it would need to be old and enormous and unmistakable. The universe, as it happens, made one. Part 5. The Balloon Over the Ice. The ruler was made about 380,000 years after the beginning, and it has been sitting in the sky ever since, waiting for someone to notice it. To understand what it is, you have to go back to a period when the universe was opaque. In the first few 100,000 years, everything was hot enough that atoms could not hold together. Electrons could not stay bound to nuclei, so matter existed as a plasma of bare nuclei and free electrons are very good at scattering light. A photon in that environment could not travel any meaningful distance before being knocked in a new direction. The whole universe was a glowing fog, and light went nowhere. That plasma was doing something remarkable while it waited. Gravity was pulling matter into the regions that happened to be slightly denser, and as those regions compressed, the radiation trapped inside them pushed back out. Compression, then rebound, then compression again. The result was sound, actual pressure waves, propagating through the plasma of the entire universe, at a speed a little over half the speed of light, because the medium was so stiff with radiation. They were standing waves, and they had a limit. A pressure wave could only travel as far as its speed, multiplied by the time available, and the time available was however long it had been since the beginning. So there was a maximum distance that any of this ringing could have covered. That distance is called the sound horizon, and it is roughly 150 megaparsecs in the units cosmologists use, though the number matters less than the fact that we can calculate it from known physics with real confidence. Then, at about 380,000 years, the temperature dropped through roughly 3,000 Kelvin. Electrons and nuclei combined into neutral hydrogen. The free electrons vanished, the fog cleared, and every photon that happened to be in flight at that moment suddenly found itself in a transparent universe with nothing to stop it. Most of them have been traveling ever since. That light is still arriving. Stretched by 13.8 billion years of expansion, it now sits in the microwave band at a temperature of 2.72548 Kelvin, and it is the most perfect blackbody spectrum ever measured in nature, more perfect than anything that has ever been produced in a laboratory. It arrives from every direction, about 411 photons in every cubic centimeter of the room you are in, uniform across the sky, to about 1 part in 100,000. The 1 part in 100,000 is the important bit. Those tiny variations are the sound waves, frozen at the moment the fog cleared. The compressions were slightly hotter, the rarefactions slightly cooler, and the pattern was preserved exactly as it stood when the plasma stopped being a plasma. So here is the situation. There is a pattern in the sky. The characteristic size of that pattern is set by the sound horizon, which we can calculate. The distance to the sky in question is set by how long the light has been traveling, which we also know. We have a ruler of known length at a known distance, and a ruler of known length at a known distance subtends a known angle, but only in flat space. If space is positively curved, the light paths from the two ends of the ruler converge on their way to us, and the ruler looks bigger than it should. If space is negatively curved, the paths diverge, and it looks smaller. The angle you measure is a direct readout of the curvature of everything between you and the plasma. It is Gauss's triangle, scaled up until it actually works, with 2 of its vertices in the early universe. In December of 1998, in Antarctica, a balloon the size of a stadium lifted a microwave telescope off the ice near McMurdo. The instrument was called Boomerang. It climbed to about 37 kilometers, above 99% of the atmosphere, into the thin, cold dark, where the microwave sky is not smeared by water vapor, and then the polar vortex took it. The circumpolar wind pattern above Antarctica in summer is a slow closed loop, and a balloon released into it travels around the continent and comes back to roughly where it started. The flight lasted 10.5 days. There was no night. The sun circled the horizon. The ice ran to every edge of the world, and the telescope stared down through its cold optics at the same patches of sky again and again, while the detectors sat at a fraction of a degree above absolute zero. When the data came back, and the team plotted the size distribution of the spots, there was a peak, a pronounced, unmistakable bump at a particular angular scale, which is what you get when a resonant sound wave freezes into a sky. And the bump was at approximately 1 degree, which is about twice the apparent width of the full moon. 1 degree was the flat space prediction, not the closed prediction, not the open prediction, flat. The results were published in 2000, and they were the first strong observational statement that the geometry of space is Euclidean, on the largest scales we can survey. Everything since has confirmed and tightened it. In the technical language, the peak is described by its position in the multipole expansion, and it sits at a value of about 220. WMAP measured it better. Then Planck, from a stable point 1.5 million kilometers out, mapped the whole sky in 9 frequency bands over 4 years, and the final analysis, combined with the imprint of the same sound waves in the distribution of galaxies, gives a curvature parameter of 0.001, plus or minus 0.002. None of this would have been possible without a result from 6 years earlier. The COBE satellite, launched in 1989, spent its first years establishing that the microwave background really is a perfect blackbody, and then in 1992, its differential radiometer detected the variations for the first time. They are about 30 millionths of a Kelvin against a background of 2.7 Kelvin. Until that detection, nobody had ever seen the pattern, and there was a genuine worry that it might not be there at all in the amount the theory required. George Smoot described the result at the press conference in terms that he has been quoted on ever since and has spent decades mildly regretting. The overstatement was forgivable. He was looking at the oldest photograph in existence. 2 details make the ruler more trustworthy than it might sound. The first is that the surface we are looking at is not really a surface. Recombination took time, so the shell has thickness, corresponding to a spread in redshift of roughly 80, which works out to a layer some tens of millions of light-years thick. The measurement survives this because the pattern is much larger than the blur. The second is that the same ruler shows up somewhere else entirely. Those frozen sound waves also left an imprint in the way galaxies cluster, a slight excess of pairs separated by the sound horizon distance, and that feature has been measured directly in galaxy surveys billions of years later in cosmic history. The same ruler at 2 wildly different ages of the universe, giving consistent answers. That is why the combined constraint is so much tighter than either measurement alone. Sit with that number for a second. 0, with an uncertainty of 2 parts in 1,000. If space is curved at all, the radius of that curvature is so large that the entire observable universe is a small and locally flat patch of it, in the same way that a football pitch is a locally flat patch of the Earth. There is an honest complication, and it deserves stating, because leaving it out would be the same kind of tidying that this whole video is arguing against. Planck's temperature and polarization data, taken by themselves, without the galaxy clustering data, actually show a mild preference for a slightly closed universe, with a curvature parameter around minus 0.04. This is real, and it is in the papers. It comes from a known degeneracy involving the amount of gravitational lensing in the maps, and it dissolves as soon as independent data is added. It is not a suppressed result, it is a well-understood feature of a likelihood surface, and it is discussed openly by the people who publish the number. But it is worth knowing that the flatness result is a combination of datasets rather than a single clean reading. That is the measurement. It took a century of theory and 40 years of instruments and several thousand people, and it is one of the finest things our species has done. The geometry of space is flat. And then, in article after article, in documentary after documentary, comes the next sentence. The universe is flat, and therefore it is infinite. That sentence is not in the data. Part 6. The step that is not in the data. The universe is flat, therefore the universe is infinite. It is one of the most repeated inferences in all of popular science, and it is wrong. Not wrong in the sense of being unlikely, or of overstating the confidence. Wrong in the sense that the conclusion does not follow from the premise at all, in the way that the premise being true would still leave the conclusion undetermined even if you had infinitely precise instruments. You can see why it feels right. Picture a flat plane. Not a flat surface with edges, like a table, but an actual mathematical plane, and picture it extending away from you in every direction. Does it stop? Of course not. Flatness in your imagination is the same thing as endlessness, because the only way you can think of for a flat plane to end is for it to have a boundary, and we established that boundaries are not allowed. Flat and unbounded therefore feels like it must mean flat and endless. Now go back to the sheet of paper we rolled into a cylinder at the beginning of the night. Roll it once, taping the left edge to the right edge. Now take the resulting tube and bring its two open ends together and join those. What you have made in your head is a shape mathematicians call a flat torus, and its properties are exactly the ones that break the inference. Its curvature is zero, everywhere. Not approximately, not on average, but precisely zero at every point, because at no stage did you stretch or compress the paper. You only joined edges that were already there. Every triangle drawn on that surface has angles summing to 180 degrees. Every circle has the circumference the formula says. Every parallel line behaves. If you were a creature living in that surface, every geometric measurement you could ever make would return the flat answer. Its area is finite. It is exactly the area of the sheet you started with, and it has no edge. Nowhere on it does the surface stop. Walk in any direction as long as you like, and you never come to a boundary, because the boundaries were joined. Flat, finite, and unbounded, all three at once, in an object simple enough to build out of a sheet of A4 and some tape. The inference is dead. Flatness does not imply infinity, and it never has. The three-dimensional version is not harder in principle, only harder to picture. Take a cube of space. Identify the left face with the right face, so that anything crossing the left face reappears at the corresponding point on the right. Do the same with the front and back, and with the top and bottom. What you have is a three-dimensional flat torus, a finite volume of space, with zero curvature everywhere, containing no boundary of any kind. Cross a face, and you come back in on the other side, still going straight, having turned nowhere. This is not a fringe construction. It is a legitimate solution of Einstein's field equations, indistinguishable in every local respect from infinite flat space. And this is the point where Riemann's sentence comes back with the weight it was always carrying. Unboundedness belongs to the relations of extent. Infinite extent belongs to the relations of measure. What we measured, with the balloon over the ice and the satellite at the stable point, was a relation of measure. It was a fact about how distances behave locally, which is the definition of curvature. The question of whether space closes back on itself is a relation of extent, and there is no local measurement that touches it. I want to be precise about how absolute this is, because it is easy to hear it as a practical difficulty rather than a structural one. It is not that distinguishing a three torus from infinite space is a hard experiment requiring better technology. It is that there is no experiment. The two spaces are locally identical. Every measurement you can perform inside a region smaller than the wrapping scale returns the same answer in both. You could have instruments 1 billion times more sensitive than Planck's, and it would make no difference, because the information you are after is not present in the local geometry at all. It is in the global connectivity, and connectivity does not leave local traces. There is a catalogue of the options, and it is finite and small, which is a pleasing thing about this corner of the subject. If space is exactly flat and finite, then it must be one of exactly 10 possible shapes. 10 compact flat three-dimensional spaces, classified completely by Hancher and Wendt in 1935, building on earlier structural theorems by Bieberbach. 6 of them are orientable, and 4 are not. Only one of the 10 is the simple cube with identified faces we just built. The others involve twists. In some of them, crossing a face and reappearing on the other side also rotates you by a quarter turn, or a half turn, or a third of a turn. In the four non-orientable cases, a complete circuit in one direction returns you mirror reversed, with your heart on the other side of your chest and every written word backwards. Nothing in general relativity forbids any of these. They are all exactly flat. They are all consistent with every measurement ever made. So what does the flatness result actually buy us? Something real and worth having. It says that if space is curved at all, the radius of that curvature is enormous, comfortably larger than the region we can see. That rules out a small closed universe of the kind Einstein originally proposed, where the wrapping would be a consequence of the curvature itself, and the whole thing would be modest in size. That is a genuine constraint on a real family of models. It is worth putting a number on how large. Translating a curvature parameter of 2 parts in 1,000 into a physical radius depends on which dataset and which convention you use, but the answer comes out in the region of 100 billion light-years or more. The observable universe has a radius of about 46.5 billion light-years, so the sphere of curvature, if there is one, is several times the size of everything we can see, and we are surveying a patch of it small enough to look perfectly flat, in exactly the way that a football pitch looks perfectly flat, while sitting on a planet 8,000 miles across. The same freedom exists for the other two geometries, which is a detail usually left out. A positively curved space is automatically finite, so people tend to treat closed and finite as synonyms. But even a positively curved space can have non-trivial topology on top of its curvature, and one of the most interesting proposals anyone ever made about the shape of the universe was exactly that. And a negatively curved space, which is usually described as infinite, does not have to be. Friedmann himself pointed out in 1924 that a negatively curved universe could be finite if it had the right topology, and there are infinitely many ways to do it, some of them extremely strange. Curvature and connectivity are independent in all three cases. Flatness is just the case where the independence is easiest to demonstrate. What it does not do is speak to the other question. Alexander Friedmann noticed this and wrote it down in his papers of 1922 and 1924. The field equations, he pointed out, determine the local curvature of space from its contents. They say nothing whatsoever about the global topology. That freedom is simply not fixed by the physics. It has to be put in by hand, as an assumption, and the assumption almost everyone makes is that space is simply connected, which is to say that it does not wrap. That assumption has no observational support. It is chosen because it is the simplest option and because it makes the equations easier, and those are decent reasons for a working default, but they are not evidence. The universe is not obliged to be convenient. There is a name for the thing we are actually trying to measure, and it is not the curvature. It is the fundamental domain, the region of space that contains exactly one copy of everything, the cube before you started identifying faces. Its size is the number that matters. If it is smaller than the region we can see, we should be able to catch the universe wrapping. If it is larger, we should not. Nobody has ever measured it. What we have are lower limits, and the lower limits come from a search that is more elegant than anything else in this story. But before the search, it is worth spending some time inside the idea, because a universe that wraps is not a mathematical curiosity that happens to be permitted. It is a place, and you could live in it, and in fact you might. Part 7. The universe is a loop. Let us stop and restack what we have, because the next stretch of the night depends on all of it being in place at once. The shape of the universe is two questions: curvature, which is local, and connectivity, which is global. Curvature is measurable from inside a small patch, and we have measured it, and space is flat to 2 parts in 1,000. Connectivity leaves no local trace of any kind, so no measurement of curvature, however precise, can settle it. An edge is not an option, because an edge would require physics to specify what happens where there is no next place, which leaves exactly two families, a universe that goes on forever and a universe that closes back on itself. Both are flat, both are unbounded, both fit every observation ever made. Now let us go and live in the second one. The clearest way in is a video game from 1979. In Asteroids, your ship flies around a rectangular screen, and when it goes off the right edge, it appears at the left edge, moving at the same speed in the same direction. Off the top, back on the bottom. There is no wall. You cannot crash into the boundary of the world because there is no boundary, and the playfield has a definite, finite area which you could measure with a ruler on the glass. That screen is a flat torus. It has all three properties at once. Zero curvature, because the geometry on it is ordinary plane geometry, and a ship crossing the middle behaves exactly like a ship crossing near an edge. Finite area, because the screen is a certain number of centimeters across. And no boundary, because the edges are joined to each other rather than to nothing. Everyone who has ever played that game has had an intuition for a finite, unbounded space and has never noticed. The mathematics that took 2,000 years to articulate is sitting in an arcade cabinet. The three-dimensional version differs only in having a third direction to wrap, and it does not have to wrap in all of them. A space could be wrapped in one direction and endless in the other two, which cosmologists call a slab, an infinite sheet of space with a finite thickness, where traveling perpendicular to the sheet brings you back around. It could be wrapped in two directions and endless in one, giving an infinite tube, or wrapped in all three, giving a finite universe with a definite total volume. I should kill a picture before it takes hold, because it is the one every article uses, and it is misleading. When people say the universe might be a torus, they show a donut. Do not accept the donut. A donut surface has curvature. It curves outward on the outside of the ring and inward around the hole, and a creature living on it could measure that curvature and find it. That is a curved space, and it is not what we are describing. The flat torus has no curvature anywhere, and it cannot be sat inside ordinary three-dimensional space without being distorted, which is precisely why we are stuck drawing donuts. The donut is a crutch for the eye. The real object is the asteroid screen, and the screen is flat, which brings us back to the map. Our cosmological maps are extraordinary. We have the microwave sky measured to millionths of a degree. We have surveys with the positions and distances of millions of galaxies. We have the expansion history, the matter content, the age. Every one of those measurements is a local measurement in the relevant sense. It describes the geometry and contents of the region we can see. They are perfect maps. And they are silent about the edges because there are no edges, and about the joins because joins do not show up in geometry. So imagine it properly. Not the flat creature this time. You. You leave the Milky Way heading straight out along some direction, and you never turn. You have unlimited time and no need to stop. The first 100 million years of travel take you out of the local group and into the space between the clusters, where the galaxies thin out into a network of filaments and enormous quiet voids. You keep going. 1 billion years. The sky ahead does not change in character. There is no thinning of the universe as you approach anything, because you are not approaching anything. 10 billion years. 100 billion. Everything around you is ordinary. Every measurement you take says the space you are in is flat and unremarkable, and looks like the space you left, because it is. And then, somewhere ahead, there is a galaxy group in your path, with a large spiral in it, and a smaller companion, and a second large spiral nearby, and a scatter of dwarfs around them, in an arrangement you have seen before. It is the local group. You are arriving at it from the far side. There was no wall. There was no moment when the geometry changed, no boundary crossed, no seam, no shudder, no sign of any kind. You went in a straight line, and the straight line brought you home, and the only thing that ever indicated the universe was finite was that you eventually finished the lap. You found your own footprints. The flat creature on the flat world found them after a walk of a few years. You found them after 100 billion, but the structure of the discovery is identical, and so is the reason nothing warned you in advance. There is a further consequence of the wrapping that most descriptions skip, and it is one of the odder ones. In a space that wraps, the notion of the distance between two objects stops being a single number. If light can reach you by going directly, and also by going the long way around the loop, then the galaxy you are looking at has two distances at once, and in a space wrapped in three directions it has many. There is a shortest path, and then a whole ladder of longer ones, corresponding to routes that circle the universe once, twice, more. Physics does not have to pick one. All of them are genuine straight lines through the space. The same is true of you. In a wrapped universe there is a shortest distance from you to yourself, measured the long way round, and it is a real physical quantity with a definite value. It is not a paradox, and it does not require duplicates of you to exist. There is one of you. There are simply many straight-line routes that begin at you and end at you, and the shortest of them is a property of the universe, as concrete as its age. And notice what is true of every point along that journey. Not one of them is the center. There is no center in a wrapped space, because every point sits in exactly the same relationship to the whole structure as every other point. There is no place where the wrapping happens, no seam where the faces are glued, because the gluing is not at a location. It is a fact about the space as a whole. If you picked a point and declared it the origin, the geometry would not agree with you, and no measurement you took anywhere would single out that point over any other. That is the thing that makes this hard to hold in the head. A finite universe is not a container. It does not feel enclosed. There is no wall in the distance, no curvature of the horizon, no sense of pressing up against anything, no direction in which things run out. From inside, a finite, unbounded universe looks precisely like an infinite one, and the reason is not that the difference is subtle, it is that the difference is not local, and everything you can feel is local. So we have arrived somewhere uncomfortable. The universe might be finite. It would look like this. The universe might be infinite. It would also look like this. And the measurement that everyone cites as settling the question is a curvature measurement, which cannot tell them apart even in principle. Except that is not quite the end of it, because there is one thing that has to go around the loop as well, and it is the only messenger we have ever had. If space wraps, then light wraps too, and light that goes all the way around arrives back here. Part 8. Then the sky has to repeat. A photon traveling through a wrapped universe does exactly what you do. It goes in a locally straight line, it crosses the fundamental domain, and it comes back in from the other side without ever turning, which means the light from a distant galaxy does not necessarily reach you by one route. It can reach you by several, and light arriving from different directions is what your eyes and your telescopes interpret as different objects in different places. So a wrapped universe has an observable signature, and it is a big one. The same object should appear more than once in the sky. This is the moment the question stops being philosophy. Up to here, we have been dealing with a possibility that is consistent with everything and detectable by nothing. Now there is a prediction, and predictions can be checked. But the prediction is not what most people picture, and getting the picture right matters, because the correct version is stranger and more useful than the cliché. People say Hall of Mirrors. Forget mirrors. There is no reflection involved anywhere in this. Reflections are what you get when light bounces off a surface, and there are no surfaces here and nothing to bounce off. What you get instead is light traveling along genuinely different straight lines, of genuinely different lengths, arriving from genuinely different directions. Those are not images of an object. They are the object, seen along several roads at once. And because the roads have different lengths, the light left at different times. That is the detail that dismantles the mirror picture completely. A mirror shows you the present. A wrapped universe shows you the past, and a different amount of past down every route. The nearest copy of our own galaxy, seen by looking along the shortest wrapping direction, would show the Milky Way as it was one full crossing time ago. If the fundamental domain were, say, 30 billion light-years across, that light left 30 billion years ago, which is more than twice the age of the universe. So in practice, that particular image could not exist. Push the domain down to something the light has had time to cross, say 10 billion light-years, and the image would show this region of space as it was 10 billion years ago, when the sun did not exist, when the galaxy was a smaller and more chaotic thing still assembling itself out of gas. You would not see yourself, you would be looking at the material you are made of, before it was you, from the outside. There is one number that governs whether any of this is visible, and it is worth naming because everything later in the night depends on it. Call it the crossing time, the size of the fundamental domain, divided by the speed of light. It is how long light takes to go around once. If the crossing time is shorter than the age of the universe, light has had time to complete a lap, and the copies exist and are in principle observable. If the crossing time is longer than the age of the universe, no light has ever finished a lap, no copies have arrived, and the sky looks exactly like the sky in an infinite universe. The wrapping would still be real. It would simply not have had time to announce itself. That is a knife edge, and it does not lie anywhere near the middle of the range of possible universes. It sits at a specific scale, and which side of it we happen to be on is not something anyone chose or predicted. It is just a fact about the size of the domain, and the size of the domain is the one thing nobody has ever measured. Now count the copies. In a space wrapped in all three directions, the fundamental domain's tile space like blocks in a lattice, stretching away in every direction. The number of copies inside a sphere of a given radius grows roughly as the cube of that radius divided by the volume of one domain. So a universe wrapped on a scale even a little smaller than our field of view would not produce a handful of duplicates you might miss. It would produce thousands of them, spread across the sky in a geometrically rigid arrangement. And the arrangement is the giveaway. This is the point that makes the whole search possible. A universe that happens by chance to contain two similar-looking galaxies is unremarkable. A universe that contains a lattice of repetitions with regular spacings and consistent relative orientations is not something chance produces. You are not looking for a coincidence. You are looking for a pattern with a rigid geometry to it. And geometry is exactly the sort of thing an algorithm can hunt for. Some of the 10 flat options make this stranger still. In several of them, the identification involves a rotation as well as a translation, so that light crossing a face comes back in rotated by a quarter turn or a third of a turn. The copies of a galaxy would then appear at different orientations, tipped relative to each other by fixed and repeating amounts. In the 4 non-orientable cases, a full circuit reverses handedness. A traveller returning from that lap would come back mirrored and would have no way at all of having noticed the moment it happened, because there is no moment. The reversal is not an event that occurs at a place. It is a global property of the route. It is also worth being clear about what a wrapped universe does not do, because people sometimes assume it would show up as some general untidiness in the data. It would not. A multiply connected space is still homogeneous and still isotropic on average. The microwave background would still be uniform across the sky to 1 part in 100,000. The expansion would proceed identically. The abundance of the light elements, the growth of structure, the ages of the oldest stars, all of it comes out the same. Topology does not disturb the physics. What it does is correlate specific pairs of directions with each other, and nothing else. It is an exceptionally quiet feature to look for. It changes nothing about the universe, except which parts of the sky are secretly the same part. And if the wrapping is uneven, the signature changes shape. A universe wrapped tightly in one direction, and loosely or not at all in the other two, would not give you a lattice of copies. It would give you a single preferred axis, with repetitions strung along it, and nothing anywhere else. That case is much harder to detect, and much harder to rule out, which is why the limits on it are considerably weaker than the limits on the fully wrapped case, and why it is still, quietly, one of the live options. There is no local experiment that could warn you about any of this. That is the point that keeps returning. Everything about the wrapping is a fact about journeys, not about neighborhoods. The idea of looking for repeated images is older than most of the physics in this video. In 1900, 15 years before general relativity, Karl Schwarzschild published a short paper asking what limits could be placed on the size of a closed universe. His reasoning was that in a small enough closed space, light from the stars would have wrapped, and we would be seeing the same stars in multiple places on the sky. Since astronomers were not obviously cataloguing the same star twice, the universe had to be at least a certain size. That is a matched image topology constraint, done with a star catalogue in 1900. The method we use now is a refinement of the argument he made. The trouble with using galaxies for this is that galaxies change. A galaxy seen along a route that is 5 billion light-years longer is a galaxy 5 billion years younger, and 5 billion years is enough to turn a quiet spiral into something you would not recognize, or to have it merge with a neighbor, or to have its star formation shut down entirely. You would be trying to match objects whose whole appearance had shifted. It is close to hopeless, and the direct searches that have been done on galaxies and clusters give only weak limits for exactly this reason. What you need is something that has not changed, something laid down at a single instant across the whole universe, still carrying the pattern it had at that instant, with no evolution to confuse the comparison. We have that. It is the light from the moment the fog cleared, and it fills the sky in every direction, and it is the same age everywhere we look. In 1998, 3 physicists worked out how to use it, and the method they came up with is one of the most elegant ideas in modern cosmology. Part 9. Somebody looked. The idea is called circles in the sky, and once you see it, you cannot unsee it. Neil Cornish, David Spergel, and Glenn Starkman published it in 1998, and it works like this. The microwave background does not come from a place, it comes from a time. Everywhere in the universe went transparent at roughly the same moment, so the light you receive tonight left from whatever region happened to be exactly the right distance away for its light to be arriving now. That region is a sphere, centered precisely on you, with a radius set by how long the light has been traveling. Every observer has one. Yours is centered on you, and nobody else's is. Now suppose space wraps, and suppose the fundamental domain is smaller than that sphere. Then your sphere is larger than the box it lives in, which means it must overlap the copies of itself. And when 2 spheres of the same size overlap, they intersect in a circle. Here is the payoff. That circle is a real physical ring of plasma in the early universe, and you are seeing it twice. Once by looking in one direction, and once by looking in another direction entirely, because the light took 2 different routes around the loop. Both views show the same ring, so both must show the same sequence of hot and cold spots, going around, in the same order. Somewhere on the sky, there would be 2 circles with identical temperature patterns. Not similar. Identical, because they are the same plasma. What makes this test so good is what it does not need. It does not need a model of how galaxies evolve, because the microwave background does not evolve. It does not need you to guess the topology in advance, because you are not fitting a specific shape. You are asking whether any matched pair exists anywhere. It does not need the pattern to be bright or unusual. It just needs two rings on the sky to carry the same sequence, and if they do, the universe wraps, and the geometry of the matched pairs tells you how. So they ran it. The computer takes the full microwave sky and starts comparing. For every possible pair of points on the sphere, at every possible circle radius, at every possible relative phase around the circle, it lines the two rings up and asks whether the temperature sequences agree. There is no clever shortcut available. The search space is enormous, and mostly it is brute force. Circles that are too small are drowned in instrument noise. Circles near the largest radii are checked against the parts of the map most damaged by the galaxy sitting in the way. Millions of comparisons run, and the statistic that measures agreement is computed for each one, and the whole distribution is compared against what random skies produce. It ran. It finished. There was nothing. Not a marginal signal, not an intriguing hint that needed better data. The distribution of matches looked exactly like the distribution you get from a sky, with no topology at all. Cornish, Spergel, Starkman, and Komatsu published it in 2004, using the first year of data from the WMAP satellite, in Physical Review Letters, under the flat title, Constraining the Topology of the Universe. The bound they quoted put the fundamental domain at something like 24 gigaparsecs across at minimum, which is a distance of roughly 78 billion light-years. Planck did it again. Better. The 2015 analysis, published as the 18th paper in that year's release under the title Background Geometry and Topology of the Universe, ran both the direct circle scan and a full likelihood computation for specific topologies. It was also the first search to use the polarization of the microwave background as well as its temperature, which matters more than it sounds, because polarization is generated at the moment of last scattering itself, and is therefore less contaminated by structures the light passed through afterwards. Cleaner data, same question. Their limits are worth stating properly, because the way they are usually reported loses the crucial word. For a cubic 3 torus, the radius of the largest sphere that fits inside the fundamental domain must be greater than 0.97 times the distance to the last scattering surface. For the slab, greater than 0.56 times that distance. The circle search on polarization alone gives the same 0.97 for the cubic case at 99% confidence. Notice what those numbers are ratios of. They are not measured against the size of the universe, because nobody knows the size of the universe. They are measured against the distance to our own last scattering surface. They are statements about our field of view. There is a subtlety in the search that turned out to matter a great deal, and at the time, almost nobody flagged it. The circle test is most sensitive when the two matched rings can be lined up cleanly. If the identification of faces involves a pure translation, the two views of the ring start at corresponding points, and the sequences line up straightforwardly. But if the identification involves a rotation as well, a twist built into the wrap, then the two views are offset in phase relative to each other. The pattern is still identical. It simply starts at a different place around the ring. Handling that properly means searching an extra dimension of possibilities for every candidate pair, and the early searches were considerably less sensitive to those cases than to the untwisted ones. So the headline result, no matched circles found, was strongest for the simplest topology and weakest for the twisted variants, which is a distinction that got flattened almost immediately in the reporting. Before we sit with that, there is a casualty to record, because for a short period this question had a real answer, and then it did not. In 2003, Jean-Pierre Luminet, Jeffrey Weeks, Alain Riazuelo, and their colleagues published a proposal in Nature. Their candidate was the Poincaré dodecahedral space. Take a dodecahedron, the 12-sided solid with pentagonal faces, and build a slightly curved version of it, and then identify each face with the opposite one after a 36-degree twist. 120 copies of that solid tile, the three-dimensional analogue of a sphere's surface. It is a genuinely beautiful object, and it had been studied by mathematicians for a century for its own sake. The reason they proposed it was not aesthetics. It made the numbers work. It predicted a specific suppression of the largest scale ripples in the microwave background, of about the size that had actually been observed. It required a universe very slightly positively curved, with the total density parameter around 1.013, which was within the error bars at the time. And it made a hard, falsifiable prediction. 6 pairs of matched circles, each about 35 degrees in radius, arranged in a specific pattern on the sky. Weeks, incidentally, is not a professional astronomer or a university physicist. He is a mathematician who works largely outside academia, on topology, and who wrote the standard popular book on the shape of space. The proposal that briefly answered the oldest question in cosmology came in part from someone whose day job was thinking about what shapes are possible at all. For about 18 months, humanity had a published, checkable, specific answer to the oldest question anyone has ever asked about the world. The universe was finite. It was 120 dodecahedra. You could go and look for the circles. People went and looked for the circles. They were not there, and subsequent data pushed the curvature closer and closer to zero, squeezing out the slight positive value the model needed. That was the end of it. There was no scandal, and no drama, and no retraction, and nothing to argue about. A beautiful idea made a specific prediction. The prediction was tested, the prediction failed, and the idea quietly left the table. It is exactly how the process is supposed to work, and it is worth noticing how much it costs when it does. So the searches came back empty, every one of them, and almost everyone reported that as the end of the story. It is not the end of the story, and the reason is the single most important thing in this video. But before we get there, we should ask why anybody bothered looking in the first place. Because they did not do it out of curiosity. They did it because there is something in the data that has never been explained. Part 10. The waves that are missing. There is a measurement you can make on the microwave sky that is simpler than almost anything else in cosmology, and it has been giving a strange answer for 30 years. Pick 2 points on the sky, separated by some angle. Compare their temperatures. Do it for every pair of points at that separation, across the whole sky, and average the result. What you get is a number describing how much the temperature at one place tells you about the temperature somewhere else that far away. Then do it again for a different angle, and again, and build up a curve. This is the 2-point angular correlation function, and it is one of the oldest tools in the subject. The standard model of cosmology makes a clear prediction for that curve. At small separations, there should be strong structure, reflecting the sound waves in the plasma. At large separations, above about 60 degrees, the correlation should be modest, but definitely not zero. There should be a gentle, persistent, measurable relationship between opposite regions of the sky. In the actual sky, above about 60 degrees, it very nearly vanishes. The correlation is not weak. It is close to absent, in a way the model does not produce. Craig Copey, Dragan Hutera, Dominic Schwartz, and Glenn Starkman quantified how unusual it is. And the answer is that a deficit this large occurs in something like 0.025% of simulated universes generated from the standard model. Roughly 1 in 4,000. The obvious response to a 1 in 4,000 result is to wait for better data, on the assumption that it is a fluke of a noisy measurement. So people waited. COBE saw it first. WMAP saw it again, with far better sensitivity and full sky coverage. Planck saw it a third time, with better still. The same team went back through the final WMAP maps and the first Planck release, and found p-values below 0.24% for the foreground cleaned maps, which is evidence at more than 3 standard deviations. 20 years of instrument improvement have made the anomaly sharper rather than softer. It helps to have a feel for the scale being discussed. 60 degrees on the sky is a third of the way from horizon to horizon. If you stand outside and hold your arms out at a wide angle, you are marking roughly the separation in question. The claim is that beyond that separation, the temperature of the early universe in one direction carries almost no information about the temperature in the other, and that this is not what the model that gets everything else right predicts. It is also worth stressing how odd it is for a result to survive this particular gauntlet. Most anomalies in cosmology do not. The history of the field is full of 2 and 3 sigma results that faded as the data improved. The apparent excess of gamma-ray bursts, the early claims of non-Gaussian structure, various short-lived peaks in this or that spectrum. The standard expectation is that a strange result at the edge of the sensitivity is a strange result about the instrument. This one has now been measured by 3 separate spacecraft, built by different teams, with different detectors, different systematics, and different failure modes. And all 3 agree that the correlation above 60 degrees is not where the model puts it. It does not sit alone. The largest scale ripple in the microwave background, the quadrupole, has less power than expected. The quadrupole and the next one up, the octupole, are aligned with each other more closely than chance comfortably allows, and their shared orientation lies suspiciously near the plane of Earth's own orbit around the Sun, which is a coincidence nobody has a good story for. That collection of oddities has been nicknamed the axis of evil in the literature, which is the sort of name that gets attached to a result when the people who found it do not believe it themselves. And there is a very natural explanation for missing correlations at large angles, which is why the topology people arrived at a run. A wave has to fit. In any finite space, there is a longest possible wavelength, the size of the space itself. You cannot have a standing wave in a room longer than the room. So in a universe with a finite fundamental domain, the very longest wavelengths are simply not available. They are not suppressed or weakened. They cannot exist, because there is nowhere to put them. And the longest wavelengths in the primordial density field are precisely what produce correlations at the largest angles on the sky. So the shape of the explanation matches the shape of the problem exactly. Correlations vanish above 60 degrees because space is not big enough to hold waves that long. It is a structural cause for a structural absence, and it does not require any new physics at all. That is what turned cosmic topology from a mathematical curiosity into an active search program in the early 2000s, and it is why Luminet's dodecahedral proposal got the reception it did. There is a human detail buried in the dodecahedral episode that is easy to miss. The model was not proposed because someone wanted the universe to be a beautiful shape. It was proposed because a specific number in the data was too small, and this particular shape produced a suppression of exactly that number, of roughly the right size, for a structural reason rather than a tuned one. That is what a good hypothesis looks like. It explains something you did not build it to explain, and it pays for the explanation by making a prediction it cannot escape. Now the honest part, which matters more than the exciting part. The first caveat is a statistical one, and it is serious. This anomaly was noticed by looking at the data. Nobody predicted in advance that the correlation function above 60 degrees would be the interesting statistic. It was chosen, at least partly, because it looked odd. When you select a test, after seeing the data, quoted significances become unreliable, because you have implicitly searched through many possible tests and reported the most extreme one. A 1 in 4,000 result found this way is not the same as a 1 in 4,000 result predicted in advance. Everyone involved knows this and says it in the papers. The second caveat is about the galaxy. The Milky Way sits in the way, glowing brightly in the microwave, and its plane has to be masked out and reconstructed. Masking damages the largest angular scales most, because those are the scales that need the whole sky to measure. A significant fraction of the debate about this anomaly is a debate about foreground subtraction, and it is not settled. The third caveat is a genuine physical effect. Photons crossing evolving gravitational potentials on the way here pick up small energy shifts, which contributes power at large angles from relatively nearby structure. At least one analysis argues that part of the observed deficit comes from a cancellation between that late-time contribution and the primordial signal, which would make the anomaly partly a coincidence rather than a clue. And the fourth caveat cannot be fixed by anyone, ever. It is called cosmic variance. At the largest angular scales, there are very few independent measurements available in principle. Not because our instruments are limited, but because there is only one sky. For the quadrupole, there are precisely 5 independent numbers in the entire universe. 5. You cannot average over more skies, because there are no more skies. The error bar on the largest scales is set by the fact that we have one sample of a random process, and no telescope ever built will improve it. So the clue is real. It has survived 3 generations of instruments, and it may be a coincidence, and we will never be able to find out for certain. That is roughly the condition the question has been in for 100 years. But the searches did happen, and they came back with nothing, and the world reported that nothing as an answer. It was not an answer, and what those null results actually establish is much narrower and much worse than almost anyone said. Part 11. What a null result actually rules out. Here is the sentence that appeared, in one form or another, in almost every account of those searches. The universe is not a torus. Cosmic topology has been ruled out. Space does not wrap. None of those statements is what the papers say, and the difference is not a technicality. What the searches tested was whether the fundamental domain is small enough to fit inside the sphere of the observable universe. That is the only configuration in which matched circles exist. If the box we live in is smaller than our field of view, our sphere of last scattering overlaps its own copies. Circles are produced, and the search finds them. If the box is larger than our field of view, the sphere does not reach the copies, no circles are produced, and the search finds nothing. Go back to those Planck limits and read what they are actually ratios of. 0.97 times the distance to the last scattering surface. 0.56 times the distance to the last scattering surface. Every number in that paper is expressed relative to our own horizon, because our own horizon is the only thing the measurement has access to. They are not statements about the universe. They are statements about the largest circle we are able to draw. So the result is this. The universe does not wrap on a scale smaller than what we can see. That is genuine knowledge, and it is worth having, and it is a great deal narrower than what was reported. And now the part that makes this the hardest turn of the night. Suppose the fundamental domain is slightly larger than our observable sphere, not enormously larger, 10% larger. In that universe, space is finite. It has a definite total volume. Light will eventually go all the way around, given enough time. Every claim in this video about wrapped universes is literally true of it, and it produces no signal, not a weak signal we would need better instruments to extract, not a marginal correlation sitting at 1 sigma waiting for more data. Nothing. Zero. The circles do not exist because the spheres do not overlap. The lattice of copies exists, but every copy is further away than the furthest thing we can see. The correlations that topology induces are all between directions that are, from here, empty. It is worth putting a concrete case on the table, because abstractions slide past. Imagine a universe whose fundamental domain is 200 billion light-years across. Space is flat. Space is finite. The total volume is a definite number, and if you had a complete inventory of everything in that volume, you would have a complete inventory of everything that exists, full stop. Light launched in a straight line would return to its starting point after 200 billion years, which is more than 14 times the current age of the universe, so no light ever has. Now ask what that universe looks like from the inside, tonight, to us. It looks like this one. Identical microwave background, identical galaxy distribution, identical expansion history, identical everything. There is no measurement that distinguishes it from an infinite universe. There is no measurement that could be built. The difference between a cosmos with a total volume and a cosmos without one is real, enormous, and completely invisible. This is what makes topology different from every other open question in physics. Most unsolved problems degrade gracefully. Dark matter gives you weaker and weaker constraints as the candidate gets harder to detect, but there is always some residual handle, some remaining corner of parameter space, some experiment that would improve the bound. Here there is a cliff. On one side of it, the signature is loud and unmistakable, and thousands of copies fill the sky. On the other side, there is nothing to measure at all, and no instrument, no technique, no amount of money or time changes that. We do not know which side of the cliff we are on. We only know we have not seen anything, which tells us we are not deep on the loud side. It gets worse, and this is the part that genuinely does not have a comforting reading. Start with the size of what we can see. The observable universe has a radius of about 46.5 billion light-years, giving a diameter of roughly 93 billion light-years, despite the universe being 13.8 billion years old. That is not a contradiction. Light that has been traveling for 13.8 billion years has been traveling through space that expanded underneath it the whole time, so the object that emitted it is now much further away than the distance the light covered. That number does grow, slowly, as light from further away has time to reach us. But there is a second boundary that does not work like that, and it is the one that matters. The expansion of the universe is accelerating. That means there is a distance beyond which space between us and an object is growing faster than light can close the gap, and a signal sent from there today will never arrive here, no matter how long we wait. That distance is the cosmic event horizon, and in the standard model it sits at roughly 16.5 billion light-years. Objects beyond it are not merely far away, they are permanently disconnected from us. Anything happening out there now is not late news, it is no news, ever. So the volume of the universe that we can ever, even in principle, gather information from is finite, and it is not growing without limit. It is approaching a ceiling, which means the search for cosmic topology has a deadline that is not about funding cycles or instrument generations. If the fundamental domain is larger than the maximum volume we will ever be able to sample, then the question of whether space wraps is not merely unanswered. It is unanswerable, permanently, from any position inside this universe, by any observer, using any technology, at any point in the entire future history of the cosmos. And the shape of space is still a definite fact. That is what I want to leave standing. The universe you are lying in tonight either wraps or it does not. There is a fact of the matter. It is finite or it is infinite, and if it is finite, it has a specific total volume, expressible as a number, and a specific fundamental domain, with a specific shape drawn from that catalogue of 10, possibly involving a quarter turn, possibly reversing handedness. All of that is either true or false right now, about the room you are in the same way that the mass of the sun is true right now. And nobody may ever be told. That is a very unusual category of thing. We are used to unknowns. Physics is mostly unknowns, and the unknowns are what people go to work on. But an unknown normally comes with an implied route. Harder experiment, better detector, longer runtime, cleverer analysis. This one may come with no route. Not a gap in our knowledge, but a gap in the availability of knowledge, where the information required has never been inside anybody's light cone and, in a universe pulling itself apart faster and faster, never will be. There is a version of the far future that makes this concrete. In roughly 100 billion years, on standard assumptions about dark energy, every galaxy outside our own gravitationally bound group will have been carried beyond the cosmic event horizon. The Milky Way and Andromeda will have merged into a single system, and around it there will be nothing observable at all. Astronomers alive then, doing careful work with excellent instruments, would find a static island of stars in an empty and unchanging sky. They would have no evidence of expansion, no microwave background bright enough to measure, and no reason whatsoever to suspect that the universe was ever anything other than what they see. They would be wrong about nearly everything, and there would be no way for them to find out. We are earlier than that, and we can see more than they will, and it is worth noticing that this is a temporary condition rather than a permanent one. The window is open now. It will not stay open. And for this particular question, it may already have been shut before anyone thought to look through it. Which sounds like the end. It is not, because the people who understand this best are not behaving as though it were. Part 12. The part that is still open. In 2024, a group of cosmologists calling themselves the Compact Collaboration published a paper in Physical Review Letters with a title that sounds mild and an argument that is not. It is called Promise of Future Searches for Cosmic Topology, and its central claim is that the microwave background data does not rule out a universe with non-trivial topology, and that whole families of possibilities have never been searched properly at all. That is an unusual thing to publish 20 years after everyone agreed the question was closed. Their case rests on the two gaps we have already walked past. The first is the twist. The original circle searches were most sensitive to the simplest case, where crossing a face translates you and nothing more. If the identification also rotates you, the matched circles are offset in phase relative to each other, and detecting them requires searching an additional dimension of possibilities for every candidate pair. The early searches did not cover that space well, so the strong statement, "no matched circles anywhere," holds firmly for the untwisted 3 torus, and much less firmly for its twisted relatives, and there are several of those, and they are just as flat and just as permitted. The second gap is the scale, and it is the one we spent the last part on. Every constraint is a ratio against our own horizon, and nothing has ever tested a domain larger than that. It is worth being clear about who is making this argument, because it would be easy to file it under contrarianism. Compact is not a fringe group. It is a working collaboration of cosmologists, including several of the people who designed and ran the original circle searches in the first place. The person who has published most persistently on the large angle anomalies is also one of the authors of the 2004 null result. This is not an outside challenge to the consensus. It is the people who produced the consensus pointing out that it has been overread. Compact went further in a follow-up published at the start of 2025, extending the analysis to lens spaces, which are a family of positively curved options. Again, the finding was not exclusion, but constraint. This much of the parameter space is closed off, this much remains, and here is exactly where the remaining space is. That is a healthier position than the one the field had settled into. Nobody is claiming a detection. What is being claimed is that the honest state of knowledge is narrower than the reported state of knowledge, and that the difference is large enough to justify going back and looking again with better tools. And the better tools are arriving, though they are not the ones you would guess. The most promising shift is a change of dimension. Every search so far has used the microwave background, which is a two-dimensional surface, a shell at a fixed distance, giving one sphere's worth of information. But a galaxy survey maps a volume. It fills in the interior of the sphere, rather than just its skin, and a volume contains far more independent information than a surface does. Topology imprints correlations throughout that volume, at every distance, not just at the shell. If you can map enough of it, precisely enough, you get many more chances to catch the pattern. That is why the next generation of surveys matters here. Euclid, launched by the European Space Agency, is mapping the shapes and distances of billions of galaxies across a third of the sky. The Nancy Grace Roman Space Telescope will add deep infrared surveys with very stable optics. SphereX is mapping the entire sky in more than 100 infrared colors, which gives distance estimates for hundreds of millions of galaxies at once. None of these was designed to look for cosmic topology. All of them produce exactly the kind of three-dimensional map the search needs. There is a practical reason the three-dimensional approach has not simply replaced the old one, and it is worth stating so the optimism stays calibrated. A galaxy survey reaches nowhere near as far as the microwave background. The shell of last scattering sits at the edge of the observable universe. The deepest galaxy surveys reach a small fraction of that distance. So a volume search trades reach for information density. It sees a much smaller region, but it sees the inside of it rather than a slice. Whether that trade is favorable depends on the size of the domain you are hunting for, which is, inconveniently, the thing you are trying to find out. The honest summary is that the two methods are sensitive to different parts of the same parameter space, and until now, only one of them has been seriously used. On the microwave side, the future is polarization. Lightbird, a planned Japanese-led mission, and balloon experiments such as Taurus are aimed at the polarized sky at large angular scales, which is the cleanest single window left. Polarization is generated at the moment of last scattering, so it carries the pattern with less contamination from everything the light passed through afterwards. There is also a theoretical case for expecting compactness, and it deserves a hearing, because the assumption of simple connectivity really is only an assumption. In quantum cosmology, several approaches treat the universe as something that has a wave function, and in those frameworks, compact spaces are often preferred, partly because they have finite volume and therefore finite action, and infinities in the action are a well-known source of trouble. In string theory, the situation is stranger still. The whole framework rests on extra dimensions being wrapped up small, so a theory in which 6 or 7 dimensions are compact and 3 are assumed not to be is a theory making an asymmetric assumption it has never justified. Brandenberger and Waffer proposed a mechanism in 1989 in which strings wound around a small compact space annihilate most efficiently in exactly 3 dimensions, allowing precisely 3 to grow large while the rest stay small. In that picture, the 3 dimensions you live in started out as wrapped dimensions and grew. Whether they ever finished unwrapping is a question, not a given. It also matters that none of this requires new physics. Every proposal on the table uses general relativity exactly as written, with the same matter content and the same expansion history. Cosmic topology is not a modification of anything. It is a choice that the equations leave open, and that everyone has been quietly making in the same direction for a century. That is a rare situation in cosmology, where most open questions require inventing a new particle or a new field. This one requires only that we stop assuming an answer we were never given. The counterargument is honest and it is strong. Inflation, the brief period of enormous expansion in the first fraction of a second, stretches everything by a factor so large that under generic assumptions, The fundamental domain is driven far beyond anything we could ever observe. If inflation happened in the way most models describe, then the topology of space is not a hard problem waiting for better data. It is a permanently unanswerable one, and the searches are a way of confirming that we are on the invisible side of the cliff rather than a way of getting an answer. Both positions are held by serious people. Neither has been able to move the other, because the thing that would settle it is a measurement nobody knows how to make. What that leaves is a question that is genuinely open, in the strict sense, not resolved, not abandoned, and still being worked on by people who understand exactly how bad the odds are. There is something worth respecting in that. The most likely outcome of the next 30 years of cosmic topology research is another set of null results and another slight tightening of a limit, expressed as a fraction of our horizon. They are going to do it anyway. Which brings us, finally, back to the question we started with. Not what shape the universe is. Why this particular question, out of every strange thing in physics, does what it does to people. Part 13. Why this one and not the others? I said at the start that the shape of the universe is the most mind-bending idea in physics, and I have been holding off on why. Here is the answer, and it comes in 4 parts, and only the last one really matters. The first reason is that the question is trivial to state. What shape is space? There is no jargon in it, no equation required, no specialist vocabulary standing between you and the thing being asked. A child can ask it, and does. Almost every other frontier problem in physics has to be translated before it can even be posed, and the translation eats most of the strangeness on the way. This one arrives intact. The second reason is that half of it is answered, and answered magnificently. 2 parts in 1,000. That is a real number, obtained by real instruments, at the end of a chain of reasoning that runs from Euclid, through Riemann, through Einstein, to a balloon over Antarctica, and a satellite 1.5 million kilometers out. Having half the question solved to that standard is what makes the other half feel like an oversight. It reads as a loose end rather than a wall, and it is not a loose end. The third reason is that the 2 halves are genuinely independent, which means that effort on one does not converge on the other. This is not how progress usually works. Normally the parts of a problem are entangled, and pushing hard on the tractable part loosens the rest. Here you could measure the curvature of space to 50 decimal places, and know precisely as much about whether it wraps as you do tonight. There is no gradient to climb. The work you can do and the work you want done are pointing in different directions. And the fourth reason, the one the others are only setting up, is what the unanswered half decides. If space is flat and does not wrap, the universe is infinite, not very large, infinite. And an infinite universe, with a finite number of ways to arrange matter in a finite volume, has a consequence that most people encounter once and then decline to think about again. Every arrangement that can occur does occur, and occurs endlessly. Somewhere out there is a region identical to this one, down to the last atom, not similar, identical, and not one of them, but an unlimited number, at unimaginable separations, each containing someone lying exactly where you are lying, hearing exactly this. That is not a fringe reading. It follows directly from infinity plus standard assumptions, and a fair number of physicists regard it as a reason to be suspicious of the assumption of infinity rather than as a discovery about the world. There is a technical version of that discomfort, and it is a live dispute rather than a matter of taste. In an infinite universe, probability becomes difficult to define. If you want to ask how likely some kind of region is, you normally count the ones that qualify and divide by the total, and in an infinite universe, both of those numbers are infinite, and the answer you get depends on the order in which you count. Cosmologists call this the measure problem, and it is not a small irritation at the edge of the subject. It undermines the ability to say that anything at all is typical or atypical. A finite universe does not have this problem. Some researchers regard that as a serious argument in favor of finiteness, on the grounds that a framework which makes its own predictions meaningless is telling you something. Others regard it as a human inconvenience that the universe is under no obligation to accommodate. Both responses are defensible, and neither is a measurement. If space is flat and wraps, then the universe is finite. There is a total volume. There is a complete inventory. Everything that exists is a list, and the list ends. There is no edge, and no center, and no outside, and yet the whole thing has a size you could write down. Light launched in a straight line comes back. Given enough time, and there is not enough time, you could visit all of it. Those are not two versions of the same universe with a parameter adjusted. They are different kinds of thing to be alive inside of, and every measurement ever made is consistent with both. Consider what it would change if you did know. Nothing, in one sense. Not a single prediction about anything you will ever observe would shift. The sun rises identically in both universes. The physics in your body runs identically. Every experiment ever performed returns the same numbers. It is the most consequential fact imaginable, and the least useful. If someone handed you the answer tomorrow, on a piece of paper, you could not check it, could not use it, and could not do anything differently on the strength of it. And yet nobody who hears the question properly is indifferent to the answer. That combination, total practical irrelevance and total refusal to stop caring, is unusual, and it is worth noticing in yourself. It suggests that what is being asked is not really a question about physics. It is a question about what kind of situation you are in. Now put yourself in the room. You are lying somewhere, in a building, on a planet, and the space around you extends outward in every direction, some distance away, perhaps 100 billion light years, perhaps 10 times that, perhaps not at all. The space you are lying in joins back onto itself. There is no wall there. If you traveled to that distance, you would find nothing but ordinary space, the same as here, with no marker and no seam. The join is not a place, it is a fact about the whole. Hold the picture for a moment longer, because it is worth being in properly. There is no horizon in this room, no far wall visible at any distance, nothing to look at that indicates a limit. In every direction, the galaxies thin out with distance, and redden with expansion, and eventually fade past the point where any instrument can register them, and the fading is smooth, and there is no line anywhere in it. If you could travel outward at any speed you liked, you would find ordinary space at every point of the journey, ordinary galaxies, ordinary physics, and no announcement of any kind at the moment you crossed from one copy of the domain into the next, because there is no such moment. The crossing is not an event, nothing happens there. It is a place exactly as unremarkable as the room you are lying in, and so is every other point along the way, and so is the point where you started. And the room is stretching. Every year the walls, if there are walls, are further away than they were, and the stretching is speeding up, so that light setting out from the far side has less and less chance of ever crossing to you. The room has a definite size. You are inside it, and there is no observation made from anywhere within it, at any time in its history, by anyone, that could establish that it does. Riemann said it in 1854, and it has taken us the whole night to earn the sentence. We must distinguish between unboundedness and infinite extent. The former belongs to the relations of extent, the latter to the relations of measure. 170 years later, with satellites and detectors and datasets he could not have imagined, we have measured the relations of measure superbly, and we have not touched the relations of extent, and we may not be able to. He was not describing a subtlety of geometry. He was describing, correctly and in advance, the exact shape of the ignorance we would still be sitting in tonight. Our maps are finished, or close to it. We know the age of the universe to 1/5%. We know its composition, its expansion history, the temperature of its oldest light to 6 figures. It is a perfect map, and it is silent about the edges, because there are no edges, and silent about the joins, because joins do not show up in a map. We may complete the survey of everything we can see, and still not know what room we have been surveying. And the creature walking in a straight line, looking for its own footprints. That was the first image tonight, and it is the last one, but it inverts on the way out. The point is not that you might find them. The point is that the lap takes longer than the universe has existed, so no light has finished it, and no traveler ever could, and the footprints are there or they are not, and the walking will never settle it. The evidence is not late. It was never going to arrive. So that is why this one. Not because it is the deepest question in physics, and not because it is the hardest. There are harder. It is because it is the only one that is simple enough for anyone to ask, half solved to 2 decimal places, unsolvable in the half that matters, and decisive about whether everything that exists is a finite thing. The shape of the universe is the most mind-bending concept in physics, because it is the one place where the answer is definitely out there, definitely real, definitely a fact about the space you are lying in right now, and quite possibly not for us. Sleep well. The room is exactly as large as it is, and it does not require you to know.